In this video, we are looking at finding the domain of a vector-valued function of r of t. Now we can look at r of t vector-valued functions in two-dimensional space or three-dimensional space. Technically, we could go to n-dimensional space, but we'll only visualize vector-valued functions in 2D and 3D. So here's just a generic vector-valued function. So this vector-valued function r of t has parametric equations x of t, y of t, and z of t. And as t increases, as t takes on all the values in its domain, we trace out a curve in three-dimensional space. So maybe this is three-dimensional space, and as t increases, we go on a path like this. It's an interesting path. That looks like fun. It looks like a roller coaster or something like that. Let's see. So as t increases, we're going this way, and that's our path. We might want to know what is the domain of this function. And again, remember how this works. R of t is taking a number. It's taking t, which is in the domain of this, just some real number, and it's sending it to an ordered triple if we're looking at three-dimensional space, an ordered pair if we're looking at two-dimensional space, an ordered n-tuple if we're looking at n-dimensional space, and it's taking this real number and it's mapping it to a single point. So r of t actually starts at the origin, and it points and it says, this is where you are at time t. And you say, well, where is that? Well, that's at x of t, y of t, z of t. And then as t increases, you're at all of these different locations. So this is actually the path that you would be on if this was your position function at time t. R of t frequently represents the position function, and t often represents time. If t doesn't represent time, you can just think of it as a variable. As that variable or parameter changes, we trace out this curve in space. But I think it's helpful to think of it in terms of motion. At a certain time, I'm at a certain location, and this is the vector that's pointing to that location. So r of t starts at the origin and it points to where you are. Okay, so I want to find the domain of this, and it's actually pretty simple. Finding the domain of this, it comes down to being able to find the domains of the three components. X of t, y of t, and z of t are just real valued functions of t. They're just Calc 1 functions, pre-algebra functions, or not pre-algebra functions, college algebra functions, pre-calculus functions, just regular functions. And we need all three of those to be well-defined at the same time. So where the domains of these three functions overlap, that's the domain of r of t. And you might remember this idea of three sets of, or three intervals overlapping. If I'm talking about where this the domain of this function and the domain of this function and the domain of this function overlap, that's called the intersection of those three domains. So we're just going to say the domain of r of t is the domain of x of t, intersected, that's represented by that upside down u, with the domain of y of t, intersected with the domain of z of t. So we need all three of those to be defined at the same time, because if I can plug in t equals 2 to these two guys, but plugging in t equals 2 to that one doesn't make sense, well then t equals 2 can't be in the domain of r. That t value has to make sense in this function and this function and this function at the same time, which is why we need the intersection. Now, one other thing that you might need to remember is how we find the domain of a real valued function. So to find the domain of x of t, y of t, and z of t, and we're going to come back to this over and over again in various chapters, you want to include, well, we're going to talk about what to exclude, excuse me. To find the domain of the real valued function, I need to think about which t's don't work. And we'll say that the domain is all the t's that are left over, all the t's that do work. So we're going to say, to find the domain, we need to exclude some t values. So we're going to exclude real numbers t that cause the following problems. Division by 0. Don't do it. You can't do it. You can't take something and divide it into no pieces. It doesn't make any sense. So don't divide anything into 0 pieces. Those t's are out. We also cannot take even roots of negative numbers. Not in the real number system. We're not dealing with complex numbers here. There's another class that's very beautiful called Complex Analysis. You can learn all about complex numbers. You can take square roots of numbers. You can take negative numbers. You can take fourth roots, all kinds of roots of negative numbers if you want to. But not in this class. We can't because you'd end up with a complex number. So no square roots, fourth roots, sixth roots, eighth roots, no even roots of negative numbers. If that's going to happen, those t values can't be in the domain. And then the last thing that we need to worry about, the third possible cause, is logarithms of negative numbers or 0. You can take the log of a positive number, even if it doesn't simplify nicely. Natural log of 17, it's well defined. Put it in my calculator, I can get a numerical approximation. Totally fine. But I cannot take the logarithm of 0, and we can't take the log of a negative number. Turns out that's a complex number too. Beautiful, interesting class, but we're not going to take logs of negative numbers in this class. So exclude anything that causes division by 0, even roots of negative numbers, or logs of negative numbers or 0. So with all that in mind, let's do an example. Say we want to find the domain of R of t, and R of t has 3 components. Now just to illustrate those 3 cases we talked about, I'm making it kind of a complicated R of t. So R of t has components t plus 1 times t minus 5, all divided by t plus 1 times t minus 2. That's its x component. Its y component is the square root of 2t plus 6, and its z component is the natural log of 9 minus t. You might say, Miss Townsend, when on earth will we ever see a particle that travels on a path that looks like that? You're absolutely right. This is very contrived, but we're using it as an example to find the domain of R of t. And those 3 things that we need to worry about. So this is x of t, and this is y of t, and this is z of t. If I want to find the domain of R of t, I need to find the domain of each of these 3 parts and then see where they overlap. So the first thing I'll do is find the domain of x of t. So the domain of x of t is going to be the set of all t in the reals such that the following is true. Let's look at it. We have those 3 things we have to worry about. We cannot divide by 0. We cannot take even roots of negative numbers. We also cannot take the log of a negative number or 0. There are no roots here. Don't have to worry about that. There are no logs here, but there is division. So we're going to have a problem whenever this denominator is 0. Now be careful. So many students, it's been a while since Calc 1, will just take that out and say the only problem occurs at x equals 2. It's not the case. If t equals 2, not x equals 2, t equals 2. When t equals 2, this is undefined, so t equals 2 is not in the domain. But this is also undefined whenever t plus 1 equals 0. This can't be 0 and this can't be 0. As long as t plus 1 is not 0, we can cancel those out. So x of t does simplify, but the t value that causes that to be 0 is still not in the domain. So before simplifying, look at this and say, denominator can't be 0. So the domain of x of t is all t in the reals such that t plus 1 is not 0, and t minus 2 is not 0. And we could write it like that, but I'd like to write it in interval notation. So let's just work that out. If t plus 1 is not 0, that means t is not equal to negative 1. And we have t minus 2 is not 0. So that means t is not equal to 2 either. So the domain of x of t includes all real numbers t except for that one and that one. If I draw it on a number line, I know it's probably been a really long time since you've drawn these things on a number line. Draw them in order, smallest to largest. That's ruled out and that's ruled out. But any other t value, that would work just fine for our x of t. So the domain of x of t is this interval. It's the union of this interval and this interval and this interval. And if we read it from left to right, we get negative infinity to negative 1, union, any x value in there. And then we're also talking about the x values in there, negative 1 to 2, and the x values in there. So that's the domain of x of t. Now the domain of y of t is very similar. You're looking for those 3 problem areas. We cannot divide by 0. Is there any division in here? I hope you said, no, Miss Townsend, there's absolutely no division in y of t, so we don't have to worry about the division by 0. Do we have an even root? I hope you said yes. There's an implied 2 there, so that is an even root. We cannot take an even root of a negative number, not in the real number system. So the domain of y of t is all real numbers t, such that this number under the square root, well, it has to be positive. We can take the square root of 7, it's fine. Even though it doesn't work out nicely, we got a calculator, we can find a numerical approximation. We can even take the square root of 0. Square root of 0 is just 0. But we cannot take the square root of negative 4 and get a real number out. We can't take the square root of any negative number and get a real number out. So this expression under the radical has to be positive or possibly 0, because we'd be okay taking the square root of 0. So we force what's under the radical to be positive or 0. So that's greater than or equal to 0, same thing. And let's see if there's anything else. We couldn't divide by 0. We can't take even roots of negative numbers. We cannot take the logarithm of a negative number 0. Are there any logs in y of t? Hope you said, no, Miss Townsend. Okay, so we're done. We're here. Okay, so this is our domain for y of t. You just have to get t by itself now. I'm going to solve that inequality by subtracting 6 from both sides, dividing by 2. It's probably been a while. If that 2 happened to be negative, don't forget, if you're dividing or multiplying an inequality by a negative number, you have to flip the direction of the inequality. So this says greater than or equal to. If that were a negative 2, it would turn into less than or equal to. But it's a positive 2, so we're fine. We get t is greater than or equal to negative 3. So on the number line, that means go to negative 3. You say anything greater than that is fine, and even negative 3 is fine. So we're shading to the right. And if I want that in interval notation, I read that from left to right, negative 3 to infinity. Okay, so that's my domain of y of t. So you find the domain of x, the domain of y, now we're going to find the domain of z. Now remember, you cannot take, or we cannot divide by 0. Any division? Nope. Okay, no problem. We cannot take an even root of a negative number. No even roots. No problem. We also cannot take the logarithm of a negative number or 0. I've got a logarithm, so we're going to have some potential problems. If this can't be negative and it can't be 0, it has to be positive. I have to take the logarithm of a positive number. So the domain is the set of all t values in the reals where this expression inside the logarithm, that's called the argument, the argument has to be positive, strictly positive. So we get that. And we're going to add t to both sides here. So you have 9 is greater than t, or if you prefer, and I prefer it, I like to put my t first. If 9 is greater than t, then t is less than 9. So you can just switch the order as long as you flip the inequality as well. So we've got the interval from negative infinity to 9, or if you prefer, you can draw it on a number line. T can't be 9 because then we'd be taking the logarithm of 0, not okay. But t can be any number less than 9, and that'd be totally fine with us. 8.99, fine. 8.999, totally cool. You just can't put in 9. Okay. All right, so now we've got these 3 domains. The domain of R of t is where all 3 of these overlap. So I need the t values to belong to all 3 of these sets at the same time in order for us to have t values in the domain of R of t. So I'm just going to write down my answer, and then we'll talk about where those 3 sets overlap. The domain of R of t is the intersection of the domain of x of t and the domain of y of t and the domain of z of t. And so we get the intersection of this so that's the domain of x of t, and this domain of y of t, and the last one, domain of z of t. Okay, I'm going to draw my 3 number lines a little bit closer together. You absolutely do not have to draw number lines. You're in Calculus 3. But if it helps you, sometimes people are visual and they need a visual aid to help them figure out the intersection of these 3 sets. So I'm just going to draw it because I think it's easier to see what's going on. This one, anything but negative 1 and 2 is fine. So that's the domain for x of t. The domain of y of t goes from negative 3, so if there's negative 1, negative 3 is going to be over here, to infinity. So that's the domain of y of t. And the domain of z of t goes all the way to 9. It doesn't include 9, but anything less than that is fine. We want to know where all 3 of these sets overlap. So this is x, that's the domain of y, and that's the domain of z. And remember, those are functions of t. I was getting lazy. I didn't want to write of t, x of t, y of t, z of t. Okay, so for the domain of R of t, I need t values that belong to all 3 sets at the same time. I hope you see that negative 3 is a dividing number. It's changing from one interval to another. If t is less than negative 3, let's say t is negative 4, just for example. Well, negative 4 is in the domain of x, it's in the domain of z, but it's not in the domain of y. So those t values that aren't in the domain of y, those can't be in the intersection. We're looking for t values that belong to all 3 sets, so these guys are ruled out. What about t equals negative 3? Well, negative 3 is in this set, and this set, and this set, so it is in the domain. And then all these guys are in there, all 3 sets, but we got another problem at negative 1. At negative 1, well, t equals negative 1 is in the domain of y and z, but not x. So that can't be in our domain. And then we're good until we get to 2. So 2 can't be in our domain, even though 2 is in the domains of these two other guys. It's not in the domain of x, so it can't be in the domain of r of t. But anything else in here is fine. And then from 2 to 9, we're good. But then at 9, we've got a problem because z is not defined anymore. And then if we go beyond 9, well, z is not defined for t greater than 9. So this is our domain. Looks kind of ugly, but that's it. It's a good example. Gave us good practice with all of the possible restrictions on domains. And then we got to practice the intersection, which is also good. So the domain is this set, union this set, union this set. So we want any t between -3 and -1. Skip -1. And then we want all the t's between -1 and 2. Skip 2. And all the t's between 2 and 9. And that is the domain of r of t. So let's recap. When you're finding the domain of r of t, you need to look at all 3 components. All 3 components need to be well defined. And in order for those to be well defined, to find the domains of these guys, you want to exclude t values that cause the 3 problems. Division by 0. Don't want to do that. We don't want to take even roots of negative numbers. Not in the real number system. And we don't want to take logs of negative numbers or 0, not in the reals. It's actually pretty cool that logs of negative numbers involve complex numbers. But exclude those guys. So you're basically solving a pre-calculus problem, finding that domain. And the calculus part comes from saying, okay, well, where do those 3 overlap? We find the intersection of those 3 sets, and this is where the original function r of t is well defined. So these are the times, these are the t values I'm allowed to put in to this original function. And I'll label it. So that's the domain of r of t.